In this video, we're going to take a look at how to prepare our data for regression. So first of all, what are the steps? And several of these items we've covered in previous videos. So we'll focus in this video on creating dummies, label encoding, and scaling the data. But nonetheless, I also want to show how that fits in the bigger picture. So the first thing we want to do is identify a need. What is it that we're trying to predict, or what is it that we're trying to model? Then we want to find the data that will support this model. Then we want to identify feature columns. In other words, what are the predictors that we can use to predict the outcome? We can use things like random forest, RFECV, backwards elimination, forward selection, exhaustive search, several different ways we can identify those columns. Next, we want to clean the data, but the reason we want to identify the columns first is we only need to clean data in those columns that are going to be used as predictors. If we're throwing away a lot of columns, we don't need to clean them. Next, we need to create dummies and do label encoding and possibly one-hot encoding, and then scale the data. After we've done that, we're going to divide the data into training and testing, and then we're going to fit the regression model, evaluate the regression model, and use the regression model. So label encoder, we'll start with that. If we have a column that has a number of strings that are used as identifiers, strings that are oftentimes repeated within that column, we can use a label encoder and it will assign a number to each of the unique strings and then effectively create a new column with those numbers instead of the strings. And we could even, if we want, overwrite the existing column with the strings with the label encoded values. Now, this is good to use for a target column because in logistic regression, we're trying to pick a categorization output. That's not a continuous output where it could be 1.3 or 1.4, but a categorization output where it's a whole number 1, 2, 3, 4. Label encoder is great for target, but it's not good for predictors. Because with predictors, we're trying to say that the value of the predictor has some impact on the outcome of that target. So if we had automatic transmission as a 0, manual transmission as a 1, and continuously variable transmission as a 2, does that mean a CVT is necessarily twice as good as a manual transmission? You see, we end up setting up a funny relationship and we have numbers that represent certain quantities, because then it appears that one feature might, or one value might be twice as heavy as another value, when really they're just numbers that happen to be assigned. So for features or predictors, we won't use label encoder, but instead we'll use dummies or one-hot encoding. This works on a slightly different way. Instead of taking that one column and assigning numbers to each of the unique strings and then saying, okay, here's a column with the numbers that align to those strings, what get dummies or one-hot does is it operates in a similar manner where it's using a column of objects or a column of strings that are used as a category, but instead of making one column with a series of numbers that represent each of those unique strings, it will make one column for each unique string, and that column is a Boolean, true or false. That way, every value is represented by a 1 or a 0, and there's not this false idea of a scale of 0, 1, 2, 3, 4, 5, 6, where 6 would have 6 times the impact as whatever happens to randomly be assigned to 1. The only thing we have to be careful here of is cross-correlation. If there are only 3 options, automatic transmission, manual transmission, and CVT, we'll end up with 3 columns. We want to drop one of those 3 columns when we're doing our prediction, because if there are only 3 possible values, then knowing the first 2 values can predict the third. In other words, if the first is true, the second is false, then the third has to be false. If the first 2 are false, the third has to be true. So we have to be aware for a bit of cross-correlation. Now, scaling is also used on features. And what we're trying to do here is take values that are of wildly different scale, like maybe age of a person versus population of a city, and put them onto the same scale. Because if not, what will happen is the item with a very large scale, like the population of a city, will overshadow all of the lower scaled items, and it will dominate the regression formula. And it could be actually that that's not a really important predictor, but those smaller scaled columns are important predictors. So what we'll do is we will do scaling here. Standard scaler is one of the most common, and what that does is it scales everything to a mean of 0 and a standard deviation of 1. In other words, it takes every value in the column, subtracts from it the mean of the column, and then divides by the standard deviation. So that will give us a fairly tight range for all of our values, no matter what the original values are. There's also min-max scaler and max ABS scaler. These are other scalars that we can use. Min-max scaler, we simply set a range, and it will scale to within that range. Max ABS scaler simply takes each element and divides it by the maximum value in that column, and that will give us a range between -1 to 1. So with that introduction, let's take a look at a Jupyter notebook I've created with a bit of data that I've created, and I can demonstrate some of these concepts. I put together just some dummy data here about rents. So first is what area is it in, a city, township, or a village? What's the income of the rent holder? Is the payment type rent, mortgage, or interest only? What's the zip code? What's the square feet? And what's the monthly payment? So the idea here is that we have something that can be label encoded, and then something that could be standard scaled. Actually, several columns that could be standard scaled, and one where we can get dummies. So let's see how this works. I've set up this notebook with the imports that we're going to need, and then I simply use PD, read CSV to read in the housing data, and we see what it starts with. Now, label encoder, I mentioned we'd only really want to use that on a target variable. Here I'm using it just on a different column to demonstrate, but nonetheless, if you see area, you see we have 3 different values, city, township, and village. So what label encoder should do is assign a unique number to city, a unique number to township, and a unique number to village. And what I first fit it, which assigns those numbers. And then I do the transformation, which applies that formula to the whole column. And I'm using that result and assigning it right back on top of that same column. So we'll effectively replace that column. Let's see what happens here. So sure enough, you see area 010102 102. So 0101 02 102. You see that it replaced each of those labels with a number. But here again, we don't really indicate that a village is somehow 2 times more important than a township in our model. So that's why we have to think about doing a dummies instead, if it's something we're going to use as a feature or a predictor. Now take a look at this. This next line, I'm just saying, look through the entire data frame and find any column where we want to make dummies out of it. It's a good thing I did this label encoder first, because if I didn't, it would take this area and it would make dummy columns out of that. But I've already converted that to numbers. So get dummies is simply going to look for any column with an object in it, and or a string, in other words, and it's going to take each of the unique values there and then make a column, a new column for that value with a Boolean. And the Boolean will be true if this name here matches what's in that column, and false if it doesn't. So let's see what happens here. So notice it removed the payment type column, which is good, so we don't have cross correlation there. It created a payment type mortgage column and a payment type rent column, and you see here false true, so this is rent, true false, so that's mortgage, false true, true false. Now here we have a false false, and why is that? Well, if remember this one, the one with $97,000 in income, that's an interest-only payment. And you notice that there's no payment type interest-only. Well, that's a good thing because remember cross-correlation. So if we do a dummies call, what we want is we wanted to make a column for every one of those values with the Boolean values in it, every one of the values in the column it's adjusting. But we want to drop one of them if there's a case of cross-correlation. In other words, in my case here, if it's not mortgage, if it's not rent, it has to be interest only. So it was smart enough to make columns, dummies columns for mortgage and for rent, but drop cross-correlation. There's a similar concept called one-hot encoding, which effectively does a similar thing. So if you see one-hot, that's the same idea as dummies. Now, We have our label encoded here. We have our dummies over here, and we still have some things of different scale from income, zip code, square feet, and monthly payment. So I'm going to scale that. And actually, you know what? I realize I need to add the area column here too. Add that. So I'm going to tell it to scale all of the columns that were not either label encoded or dummy encoded. And let's see what we get. So I'll take off that last item there. And let's see what we get. Okay. So you see we have 1, 2, 3, 4 values for each of these open and closed square brackets. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9 square bracket sets. So if we take a look up at our data set, sure enough, we have 9 rows, which is represented here. And then we took out area, we took out monthly payment, mortgage, and rent. That leaves income, zip code, square feet, monthly payment, which is 4 columns. And sure enough, you see down here there are 4 columns. So you see the scalar effectively just worked on those columns that we gave it, and it did that subtract from the mean of the column and then divide by the standard deviation. So from income to zip code to square feet, these numbers are all now on the same scale, and next we're ready to do some regression. So I hope you found this video helpful. I look forward to reading your comments. Thank you.